Ever pondered why understanding the confusion matrix holds such importance in machine learning? Well, let's get this straight. The confusion matrix is a powerful tool, a cornerstone in the realm of machine learning and artificial intelligence, and here's why. The confusion matrix, also known as an error matrix, is a specific table layout that allows visualization of the performance of an algorithm, particularly in supervised learning. It plays a pivotal role in evaluating the performance of a classification model, which is a type of machine learning model that predicts discrete values, such as whether an email is spam or not. But why is it so special? The answer lies in its ability to provide a comprehensive analysis of a model's performance. While accuracy is an important metric, it does not always paint the full picture. For instance, consider a model that predicts whether or not someone has a rare disease. If the disease only affects 1 in 1,000 people, a model could achieve 99.9% accuracy by simply predicting that no one has the disease. Yet it would fail to identify the very cases it was designed to detect. This is where the confusion matrix steps in, turning the tables by offering a more detailed analysis. It provides 4 key metrics: true positives, true negatives, false positives, and false negatives. These metrics not only allow us to assess the accuracy, but also the precision, recall, and F1 score of the model. It helps to identify where the model is succeeding and where it's falling short, enabling us to fine-tune it for better performance. Furthermore, despite its name, the confusion matrix helps to reduce confusion. It helps us understand the types of errors our model is making, guiding us towards more effective solutions. So, you see, understanding the confusion matrix is not just an option, but a necessity in machine learning. It's a compass, pointing us in the right direction, ensuring we're not just chasing high accuracy, but a truly effective model. Now the question arises, what exactly is a confusion matrix? Well, in the realm of machine learning, the confusion matrix, sometimes also known as an error matrix, is a specific table layout that visualizes the performance of an algorithm, typically a supervised learning one. Its primary function is to highlight the correct and incorrect predictions made by a classification model. Quite a handy tool, isn't it? The confusion matrix is structured into 4 essential components. Picture a square divided into 4 smaller squares. The top left square represents true positives, or TP. These are instances where the model correctly predicted the positive class. For example, imagine we have an email spam filter. A true positive would be when the filter correctly identifies a spam email. The top right square is for false positives, or FP. These are occasions when the model incorrectly predicted the positive class. So going back to our spam filter, a false positive would be when a non-spam email is incorrectly marked as spam. The bottom left square represents false negatives, or FN. These are instances when the model incorrectly predicted the negative class. In our example, it would mean a spam email slips through, marked as non-spam by the filter. And finally, the bottom right square is for true negatives, or TN. These are occasions when the model correctly predicted the negative class. So, a true negative would be when the filter correctly identifies a non-spam email. So, when you look at a confusion matrix, you're really looking at a snapshot of how well your model is performing, where it's succeeding and where it's making mistakes. It's a way to measure not just how often your model is right, but also where and how it's wrong. And that, in essence, is the confusion matrix, a simple yet powerful tool for evaluating classification models. Remember, understanding the confusion matrix is a crucial step in refining and improving your machine learning models. Understanding the confusion matrix is one thing, but interpreting it is another. So let's dive right in. The confusion matrix at first glance might look like a jumble of numbers, but in reality, it's a treasure trove of insights about your model's performance. Each component of the matrix has a story to tell. At its core, the matrix is divided into 4 parts: true positives, true negatives, false positives, and false negatives. True positives are cases where your model correctly predicted the positive class. For instance, if we're building a spam detector, true positives would be the spam emails that were correctly identified. True negatives, on the other hand, are cases where your model correctly predicted the negative class. In our example, these would be the non-spam emails that were correctly identified as such. False positives, often called type 1 errors, are instances where the model incorrectly predicted the positive class. These are the non-spam emails that our model mistakenly flagged as spam. And finally, false negatives or type 2 errors are instances where the model incorrectly predicted the negative class. These are the spam emails that slipped through our model undetected. These 4 components together give us a comprehensive understanding of our model's performance. But that's not all. The confusion matrix can also help us identify if our model is suffering from class imbalance. If we notice that our model is correctly identifying the majority class, but struggling with the minority class, it's a clear sign of a class imbalance problem. And here's the brilliant part. The confusion matrix doesn't just help us diagnose these issues, it also guides us on the steps we need to take to improve our model. For example, if we notice a high number of false positives, we might need to adjust our model's threshold for classifying a positive instance. Interpreting the confusion matrix, therefore, allows us to diagnose the performance of our model and take necessary steps to improve it. It's the compass guiding us through the complex terrain of machine learning. As we wrap up, it's time to summarize what we've learned about the confusion matrix. This mighty tool is more than just a grid. It's a key to understanding the performance of a machine learning model. Let's recap. The confusion matrix, at its core, is a simple yet powerful structure made up of 4 components: true positives, true negatives, false positives, and false negatives. Each of these components represents an outcome of our model's predictions. True positives and true negatives are the instances where our model hit the nail on the head. It predicted correctly. False positives and false negatives, on the other hand, represent the times our model missed the mark. It predicted incorrectly. But the real magic of the confusion matrix lies not just in its structure, but in how it's interpreted. It's not enough to just look at the number of correct predictions. A model's accuracy, the confusion matrix pushes us to go beyond that. It encourages us to look at precision, recall, and the F1 score. These metrics give us a more nuanced view of our model's performance. They help us understand not just how often our model is right, but how it's right and how it's wrong. Remember, a model that simply guesses the majority class will have a high accuracy but low precision and recall. That's why the confusion matrix is so important. It gives us a complete picture. It shows us the trade-off between precision and recall, helping us make informed decisions about our model. In the realm of machine learning, there are few tools as straightforward and insightful as the confusion matrix. It's not just about calculating accuracy, it's about understanding performance in a comprehensive way. The confusion matrix helps us to not just build models, but to build better models. And there you have it, a comprehensive understanding of the confusion matrix. Remember, a model is only as good as our ability to understand and interpret its performance. And for that, the confusion matrix is an invaluable tool.